Um, I should say, begin with a disclaimer, which is that both quantum physics and coffee are relatively recent interests of mine. Um, and and let's move on now. So, okay, so before we get too far into this, I would like to say something about my collaborators. So Eric Hiltunen is my postdoc now at Yale. Jeremy Hoskins is my former graduate student, who's now an assistant professor at Chicago. Jason and Monis need no introduction. Joe Chrysler was my graduate student and is now a postdoc at Columbia, and Peng Wang is my current graduate student. So these are the people who have something to do with what I'm going to tell you today. So, but first, let me begin with the backstory. So for many years, I have made a living working on optics and random media and related inverse problems. This is what Jason was telling you about. And all of this is implicitly based on the idea that light behaves classically. Maxwell equations are enough to understand the kinds of phenomena I have typically thought about. But very recently, I've become interested in what happens for quantum states of light in similar kinds of settings. And one could view this, I suppose, somewhat generously as a midlife crisis. But I think of this as having seen the light, so to speak. Okay, now, there are all kinds of quantum many-body problems that are hiding in what I'm going to discuss. But underneath the hood, it turns out that there are opportunities to do some mathematics. Now, I'm well aware that I'm talking to physicists, so let me begin with what I think of as a somewhat opportune quote from Gibbs, who my employer has asked me to remind you was the original Yaley. So he says, maybe you can all read better than I can, but he says, if I have had any success in mathematical physics, it is, I think, because I have been able to dodge mathematical difficulty. So that is part of the theme for today's talk. Okay, so let me begin with classical optics to use it as a way of staging what will come next. And to do that, I'm going to start with an experiment. Now, this experiment was done in my kitchen some time ago when my daughter was 8 years old. She was a very capable lab assistant. She's now a senior in college studying physical anthropology. I've discovered that the word physical here has a somewhat different meaning than it does for us. In any case, the experiment works as follows. So we start with a glass of water and a laser pointer. And you can see that it's on because the beam reflects against the back wall. Now we add a couple of drops of milk and a few more and a few more and a few more. In each of these frames, the medium is increasingly scattering. So here we can really see the beam. It hasn't scattered much. And eventually, multiple scattering of light sets in, and the light behaves as if it's diffuse. Okay. There are similar phenomena for electrons that I know that you guys are all very familiar with. So let me remind you, of course, that in this experiment, the little particles that come from the milk undergo some Brownian motion. And we don't really know where they are. So it's somewhat helpful to think of the medium as random. And this is random in the sense that statistical physicists usually think of randomness, a kind of subjective notion of randomness, if you will. So let's take this a little bit further, and let me show you a picture of what's called a speckle pattern. So this is, if you like, a picture of that glass of milk taken with a very, very fast camera. So you can see one realization of the disorder. And this speckle pattern is obtained with coherent illumination. And you can see the little bright and dark spots. And if you know something about speckle, then you know that understanding what happens in any given speckle pattern is a hard thing to do, but understanding its statistics is a different matter. Okay. So what you see on the right-hand side is an average over many, many speckle patterns. And that is quite a lot like the picture of the diffuse light that you saw. Okay. So if one understands something about how multiple scattering of light works, then there are all kinds of nice applications. The ones that are closest to my heart have to do with imaging. So this is an experiment done in the laboratory of my colleague at Yale, Wei Cao. And what you can see here, well, I'm not an experimentalist, but what I see here is a sample which scatters light, an incident beam, and a speckle pattern. So you can think about doing this experiment backwards. So use reciprocity to adjust the phases of the incident beam. And what you see after it passes through the sample is something like a spot. It's not diffraction limited, but it's certainly focused. Okay. A related question, I spent a lot of time in France, so this picture seems to have some utility, is this one. So on a cloudy day, you see something like this. If you look at the bottom, the image is pretty clear. And as you move up, there is more scattering until the top of the Eiffel Tower is somehow obscured. This is a situation in which there is multiple scattering of light. And this presents some kind of fundamental impediment to imaging, if you think about it in a sort of ray optics setting. So what can we do about that? Well, one way to handle problems like this, which was of great interest in biomedical optics, is what's called optical tomography. So you do an experiment in which light is incident on a highly scattering medium. This is a kind of mathematicians or physicists' idea of what a patient is. So this is milk with a few tumors in it, some absorbing inhomogeneities. The light is focused onto a camera. So there may be 1 million pixels in that camera. And then you can scan the beam 10 to the 4 times is not hard to do in a few minutes. And you get a picture of, which is somewhat hard to interpret. It looks a little bit like that Eiffel Tower, but over and over and over again, and with much more scattering. Another way to say this is that the sample here is something like 100 transport lengths in size. So a transport length might be 1 millimeter in tissue. So this is 10 centimeters of tissue. Okay. So the chance of making an image by some kind of direct imaging is kind of hopeless. Even mathematically, it's kind of hopeless, but there are some possibilities here. And this is what's been a major interest of mine over the years, less so these days, which is how to turn data like this into images by solving some kind of inverse problem. Some modest progress can be made. This is an example of some reconstructions that were actually done at Penn. Charlie remembers these days, I think. Oh, Charlie. So this is a bar target. This is a centimeter across, and you can see that you can see sort of sub-centimeter features until the whole thing breaks down. Still, this is in the middle of that sample, and you would never be able to see this just by some kind of direct imaging. Okay, so these are examples of things that you can do with classical light. And before I get too far into the talk, I should say a few things a little bit more, that are a little bit more precise. So there are some important scales, length scales, to keep in mind here. So of course, the smallest, the most fundamental for our purposes is the wavelength of light. Then we have, within what's called radiative transport theory, the scale of the scattering length. So roughly speaking, you should think of some kind of geometrical optics picture in which light travels by means of rays, which then scatter from particles, change direction, and so on. Okay? Little billiard balls of light. After many, many, many scattering events, then something like this can be, a process of this kind can be described by diffusion. And for all of this to work properly, there needs to be a separation of scales, where the macroscopic size of the system is large compared to some scattering length, which is again large compared to the wavelength. Okay. A little bit more mathematically now, at microscopic scales, we have a wave equation. There's a coefficient which you can think of as just the dielectric permittivity of the material. I'm talking purely about scalar waves. This is for mathematical convenience. There are physical effects that arise due to polarization in the near field and so on, but they won't be explicitly part of this talk. At somewhat longer scales, at mesoscopic scales, and I'm intentionally trying to use language here, which I hope is reminiscent of the electronic setting, then we no longer talk about the field itself, but we talk about something called the specific intensity. I'll be a little bit more precise about that in a moment. But this is, roughly speaking, the intensity of light at a point in space that's traveling in a direction, which I call k here. And it obeys what's called the radiative transport equation in this business, which is somewhat analogous to a Boltzmann equation in your line of work. And physically, the most important thing to say here is that there are no collisions between electrons. There are no collisions between little particles of light. So this equation is linear. And what it does is express the gains and losses, the conservation, if you will, of the specific intensity due to scattering. Okay, so I think you can all recognize this. This is a transport term, and on the right-hand side, there is a term that accounts for the gains and losses. And this little scattering kernel here is, roughly speaking, the differential scattering cross-section for an event that goes in one direction and then comes out in another. Okay, so it has to integrate up to 1. Then at very long scales, where in some sense the wave loses track of where it has been over a scale of the transport length, then one can write a diffusion equation. And this diffusion equation is in terms of some kind of average, if you will, angular average of the specific intensity. So the sort of main idea here is that in a disordered system, we can view the study of waves and random media as in the following way. We can think of averaging of randomness. I'm just going to read this. Averaging of randomness at the microscopic level leads to deterministic behavior at the macroscopic level. This is kind of a theme in this business. Okay, now we have 3 different pictures of how light moves through some kind of complex medium. And naturally, one could ask how to relate all of them together. So this is a long story. And Remy Carminati and I have written a book about this, which just appeared a year ago. I'm obligated to say this in every talk I give for the next 5 years. I'll let you decide whether or not it's useful. But the key point is that this radiative transport equation can be derived in 2 ways. So one way is familiar to physicists, and it involves diagrammatic perturbation theory and ladder diagrams and so on. There's another way which mathematicians like, which is a kind of high-frequency asymptotics. Both ways make use of the Wigner transform in an essential way, the Wigner transform being some description of how field correlations work. Now, one thing you might have noticed is, of course, is that the wave equation is somehow invariant under time reversal, but the transport equation is not. I'm assuming here, of course, that epsilon here is purely real, so there are no losses in the wave equation to begin with. So this is reminiscent of how it is that you get Boltzmann equations from underlying microscopic dynamics, right? The sort of question of the arrow of time and so on. Now, because everything here is somehow linear, it's much easier to answer this question than it is in the non-equilibrium statistical mechanics setting. And what you can see, what is sort of explained in this book with Remy, is that averaging over the random medium leads to a loss of time reversal invariance in an essential way. Okay, so once you understand the basic ingredients, there are lots of phenomena that can be explained. And I've just given a partial list. So there's the notion of coherent backscattering, sometimes called weak localization in the electronic literature. Speckle correlation, well, we've talked a little bit about that already. That's something which you can't explain with transport theory. You really need to think about the underlying wave physics. Anderson localization. Importantly, this is quite different for scalar waves and for electromagnetic waves because of the presence of the near field. I'm not an expert on this, and this is an evolving topic, but it's worth noting. For the same reason, near field effects can play an important role in all of this. They modify, if properly taken into account, the statistics of speckle patterns and so forth. And then there are lots of applications to imaging, seeing through media that are opaque. Okay, so I now want to move on to quantum optics and try to talk about how some of these same ideas come up in this context. Are there any questions before we move on? I'm happy to be interrupted.
Okay, there's one. You were mentioning this randomness breaks the universal symmetry.
Yes.
The universal symmetry is already broken now if you have the magnetic field.
That's correct. There's no magnetic field here. It's a scalar wave.
Yes. Do you think you can extend everything that you were talking about computationally?
Oh, yes, but sure. But, and I should say that's kind of a classical subject in this business, going back more than 30 years. Okay, that's a good question. Thank you. Okay, quantum optics. So somehow, as we've seen, standard radiative transport theory is based on classical theories of light propagation. And the question I would like to think about today is, are there quantum effects that somehow could play a role here? So I'm going to break this up into two types of processes, one involving single photons, which not so surprisingly are not so quantum, but you can still understand them. And then two sorts of ideas involving two photon states. Here I'm particularly interested in understanding what happens to their entanglement as they interact with the medium. Okay. To answer these kinds of questions, because we are dealing with many-body problems in a certain sense, we need some new mathematical tools, or at least that's what I'm going to try and sell you. And these tools are, in some sense, in a nutshell, somehow non-local PDEs. They involve non-local PDEs with random coefficients. Okay, so this is not the usual formulation of quantum optics, and I'll try to explain how this comes about and why we think that there are some advantages to looking at things through this lens. Okay, so let me start with a very basic model, which is sometimes attributed to Dickey. I'm not really sure about the attribution. I believe that Arnold's law is probably correct in this case. But in any event, what we have here is a model for the interaction of a quantized scalar field with a collection of stationary two-level atoms. Okay? And there are three terms in the Hamiltonian that I hope you will recognize. So the first term is just the Hamiltonian of the free field itself, right? This is the sort of oscillator representation of this thing into modes, each mode of which has energy h bar omega k and so on. The second term represents the atoms, okay? So these sigmas are the lowering operators for the atom, right? They take an atom which is in its excited state and lower it to its ground state. All of the atoms here are assumed to be identical, to have a transition frequency, or sometimes called a resonance frequency, capital omega. And then we have an interaction term, which bilinearly couples the creation and annihilation operators to the raising and lowering operators. It's Hermitian, and it involves the positions of the atoms. There's also an overall coupling constant, which I have included. It tells you how strongly they interact. There are terms here that have not been included. If you know some quantum optics, then we are leaving out the sort of non-resonant terms. We've made a so-called rotating wave approximation. I can discuss the implications of that later on, but they're not severe for our purposes. But I will make the following physical point. The atoms here interact solely through their coupling to the field. There are no dipole-dipole interactions that have been included in this story. Okay. If we were thinking about true electromagnetic fields, this would become important because one over r cubed dependence of that interaction mimics the 1 over r cubed near field decay of the fields themselves. But here the fields are purely radiative. And so whatever corrections that might come from such a dipole-dipole interaction, as long as the atoms are not too close together, can be thought of as small. Okay, so let's begin with single photons. So here we have a single excitation state. And this is the vacuum of the combined atom and field system. So the first term involves the creation of a photon with wave vector k with some amplitude alpha k. And the second term involves the excitation of an atom with amplitude beta j. Now, the Schrodinger equation immediately tells us how these amplitudes evolve in time. And they obey this system of equations. Okay. I will make the important point here that the number of excitations in this system is conserved. So if you like, you can either excite an atom or you can excite a field mode. You can sometimes think about entangling the atoms in some way. But there is only one photon in the problem in some sense. Okay. So here we go. We have a system of equations. These are completely standard, and probably go back to the time of Dickey. So in some sense, the most fundamental process that we could think about here happens when we have only a single atom. And this is the process of spontaneous emission. So let me remind you of something you learned in kindergarten. So suppose we have a single atom, which is initially in its excited state. Then the atom, of course, if there was nothing else in the universe, if there was no electromagnetic field around, the atom would simply, up to some phase, stay there forever, right? But even if the electromagnetic field is in its vacuum, the atom will decay. And the rate at which it decays is sort of exponential in time. There's a caveat here, with a constant, with a rate constant or inverse lifetime, which is related to all of the obvious quantities in the problem: the strength of the coupling, the size of the gap, and so forth. Okay. This result is one of the earliest in sort of pre-renormalization quantum electrodynamics due to Wigner and Weisskopf. This one I'm fairly sure is true, this attribution, I mean, because I've actually looked at the paper. And even though I can't read it in German, one can see the formulas. So to get this formula, you need to do something. In modern language, you need to make a pole approximation, or a quasi-particle pole approximation, where you evaluate the self-energy at the atomic transition frequency. Once you do this, the exponential decay ensues. Now, it's long been known that that's not the full story, that exponential decay is corrected and so on, until relatively recently, the observation of the non-exponential contributions to this were hard to make. But experiments are getting better. Okay, what happens if you have many atoms? So then, and this is a long and interesting story. I know we have experts, local experts in the audience. The spontaneous emission that we have becomes somehow cooperative. So the atoms conspire with one another. And the dynamics that ensues is quite complicated. So very roughly, it depends on the size of the system. For very small systems, this is essentially what Dickey was thinking about, in which all of the atoms are sort of crowded together. There is an exponential decay of the emission, which goes roughly at a rate which is n times the single atom rate, where n is the number of atoms. But for large systems, there can be oscillations and decay. Now, to study this problem computationally is quite challenging. I mean, just if you think about how many equations there are here, there are as many as there are atoms. And so people can do simulations with thousands of atoms. And that may be enough to see and understand a lot of the physics, but it doesn't provide a lot of analytical understanding of what's going on. Okay, so now, on the other hand, sort of morally, this is just, as far as the photon is concerned, just classical optics. And one can see this by eliminating the alphas, which, as you recall, are the amplitudes for the field modes. And if you do this, you wind up with an equation just for the betas, which are the atomic amplitudes. And here you have to make a Markov approximation, which in some sense ignores the history dependence of the betas. And this is thought to hold in very, very large systems. I say thought to hold because the analysis of it, as far as I understand it, is not very systematic. It's not so much an approximation as a kind of ansatz. So if you look at these equations carefully, what you realize is that they are just the coupled dipole equations in classical optical physics, where you think of light as interacting with a point scatterer. Now, the nature of the point scatterer, of course, is quite different here than it is in classical optics, where you have to sort of put that in by hand. But what this tells you is there's not a lot of quantum mechanics in this problem. So where is the quantum mechanics? Okay. In some sense, it's in the atoms. But if we really want to see quantum behavior, we need to look at more photons. Okay. Now, this is a nice picture, which comes from Scully's group. So he was very interested in a kind of rebranding of some of the things that Dickey did. So he calls this single photon superradiance. And the idea is the following. If you have just one atom, or a small, very, very small number of atoms, then its excited state decays exponentially. And the radiation pattern that comes out is largely isotropic. Now, if you have many atoms, then you can see that the decay is faster. This is the super in superradiance. In fact, I think he had a paper with that title. And the radiation pattern is more anisotropic. And finally, if you have a lot of atoms, then the behavior is no longer exponential, but in fact involves a kind of oscillation and decay. All right. These things are all based on simulations. Here's the real world. I apologize, I can't tell you the real details of this experiment, except to note that it's relatively recent. And it comes from the Kaiser group in Paris. So here's a collection of cold atoms, so they don't move around very much. You send some light to get them going. This has to be a kind of weak pulse. You look at an angle, and you measure the intensity in that angle. And what you see is that there's a flash. This is the so-called superradiant flash. And then there's decay and some oscillations. As far as I know, to do a similar experiment with 2 photons would be very, very challenging. And it's possible that there are such experiments, but I don't know of them. I know some experiments like this were planned pre-pandemic.
But I'm sorry, may I ask a question for orientation?
Sure.
So in this experiment, at time 0, the atoms are all in their ground state.
No, they get excited.
No, wait. At time 0.
I see. Yes.
So at time 0, they're in their ground state, and your incident pulse is doing 2 jobs. One is that it's, well, your incident pulse is in first instance simply exciting some or all of the atoms to a higher state.
Yes.
After which there's dynamics.
That's right.
And should I view this experiment as the job of the incident pulse really is just to excite some fraction of atoms, and then it passes through and it's gone on time scales which are short compared to this T gamma?
That's my understanding of it.
Okay. So then where does the 1 photon and 2 photons come? Because I mean, once I have a problem with
Sure.
a bunch of atoms.
Sure. So we're going to get very far beyond my understanding of this experiment very quickly.
Well,
But conceptually, this is a very weak pulse. Maybe it has only 1 wiggle in it.
No, but my question was the mathematical one of why is that essential to the analysis that you previously did?
Why is what essential?
The weak pulse for 2 photons. I mean, to me, weak pulse means that I just excite only a small fraction of these atoms to their excited state, and then I let it go.
Yes.
And I could have a mathematical problem where I excite all of them, problem where I just excite all of them and I let it go. And where's the mathematical complication? That's presumably what you're getting to.
It isn't, but I'll try to answer the question. So whatever theory I've told you about makes some assumptions about initial conditions of the amplitudes. And it assumes that the field is in its ground state and 1 atom is excited. Okay, so there is no accounting for how the pulse propagates through the medium or interacts with it in any way. This is all accounted for by means of these initial conditions. Now, it is possible to set different initial conditions. For instance, one could in the lingo of Scully, create a timed Dickey state, which is a kind of entangled state of all of the atoms. And then the dynamics are slightly more complicated, but in the end, there's not so much that's different. They sort of forget their history, and then the state decays. I don't know what this corresponds to in reality. I borrowed this slide.
But I'm sorry to hold you up.
No, it's okay.
Dickey's original problem was I take n atoms all in their excited state, and I ask how fast do those vectors decay.
That's right.
And now you were telling me here that the problem that you're dealing with is only 1 atom.
That's right.
That's the connection I'm missing.
Oh, I'm sorry. Yeah. That's exactly right. So in Dickey's paper, which I must admit I haven't read, it's exactly what you say. All of the atoms are in an excited state, and they're all packed together at a point.
Right. Yeah.
And then some analysis is done. And roughly speaking, what's found is that they decay faster than they would if they were alone. Okay. So to follow the line of thought that I'm going to get to, the first thing to do is to try and understand what happens with single excitations. And it turns out that Scully and his colleagues were there first, but using entirely classical methods, which in some sense have no quantum mechanics in them at all. And this is what you see. So nothing I have shown you so far is anything other than my own interpretation of what I have read.
But it sounds like I should forget Hickey for the moment.
You should.
That was my problem.
Yeah. But his Hamiltonian,
Yeah.
eponymously named or otherwise, is important for us.
Okay, right. Sorry to hold you up.
No, it's okay. It's the usual story. I have learned that if there's a question, everybody has the same question. So, okay. Now, I don't know of experiments, maybe there are, in which two photons are put into the system. You imagine some kind of spontaneous parametric down conversion. You have a tangled pair, they go in, they scatter, they do whatever they do, and then you measure coincidences. That's a difficult experiment. I have a colleague at Michigan who tried to set this up and was unsuccessful, largely because there are so many modes, if you will, that these photons can be in. If you put two of them into a fiber, where there are maybe only a couple of hundred modes, sometimes you can do things. Okay. So, all right. So now I'm going to tell you about how I think about these kinds of things. And the claim, for better or worse, is that if you want to think about random media and some other things too, you need some new mathematical tools. So the first observation is, wouldn't it be nice to treat the atoms and the field on the same footing? By which I mean, we quantize the field in some kind of, in Fourier space, if you will, and the atoms are sitting at defined points. So let's try to do everything together. So the Hamiltonian of the field is this guy you've seen before, right? It's this sort of oscillator representation. And I will point out that the frequency here is just proportional to the length of the wave vector k. So let's do something innocuous. Let's define 5x to be the Fourier transform of this annihilation operator of the field. And the usual commutation relations tell us that we have the commutation relations of a Bose field here. Now let me be careful. This phi is not self-adjoint. Okay, it's introduced purely for mathematical convenience. Okay, so let's see what happens if we do this. Well, the Hamiltonian, if you write it in real space, looks a bit odd. It, of course, contains phi dagger phi, as you would expect, but then the energy part involves the square root of the Laplacian. Okay, and the reason for that is because the modulus of k is the Fourier multiplier of that operator. Okay, now if you look at this thing as a Hamiltonian, or at least when we first found it, I was a bit disturbed because it's not local. But of course, you really shouldn't think of it this way because phi is not really a Bose field. It's just something that is a proxy for such a thing in a certain sense. Okay, so this guy is non-local, and it has a nice spatial representation where you can see the non-locality explicitly. Okay, so that's the Hamiltonian of the electromagnetic field for us. Okay, the total Hamiltonian you can write down almost by inspection at this point. So this is the field. These are the atoms. They now have a number density rho. So this could be just some delta functions, or it could be something else, some continuous thing. And then we have interactions, which are again bilinear in the sigmas and the phis.
So wait, I'm sorry, may I ask another question going back?
Sure.
And the way I was taught to think about these things, the A operator
Yes.
creates is connected to the vector potential. So there are
Yes.
issues with gauge invariance.
That's right.
The A is not a field, and the phi is therefore not a field.
Correct.
So how does that propagate into the real space?
So it's a good question. it's a scalar model. So you should suspend disbelief.
Okay.
And then we can talk later.
Okay.
Okay, adding to that, maybe you are right to talk later. The problem is that the initial Hamiltonian is gauge dependent.
Not in this model.
That model is gauge dependent.
What is the gauge transformation?
But if now you do all these fundamental transformations, the
Yep.
Dicke model is known to be gauge dependent. It doesn't reproduce the underlying.
But what is the gauge transformation in the Dicke Hamiltonian you're referring to?
Just go from the velocity gauge to the length gauge.
I don't know. I'm afraid I don't know what that means.
You're doing the dipole approximation.
Yes.
Which is a long way.
It is.
And then you're going to have all atoms react. One atom heating, which is a dipole.
That's right.
Another one. Then you can do the standard gauge transformation in Maxwell equations.
But there are no Maxwell equations here.
But here, if I may suggest, I think that the answer to this line of discussion is that for the moment we should suspend disbelief. I think there are issues floating around in this of gauge transformations and representation of physical problems. And John wants to tell us about this theory, which he would say is well defined in terms of this theory.
That's right.
We can discuss its connection.
And we can discuss. We can discuss.
I agree with that. I think
Yeah.
it's a connection just linked to the Dicke.
Yeah.
Only to the Dicke.
Yes, and in fact, everything I'm going to tell you, I know how to do for electromagnetic waves. It's just a matter of bookkeeping. Okay, but in the spirit of doing things simply, we work with this guy. By the way, this is very common in quantum optics. Okay.
Sorry, John, can you remind us what n is again?
What is n? Oh, n is the spatial dimension,
Okay, so basically,
also known as d.
so this is singular, right?
That's right. So, yeah, there's a principal value I could write here, but I didn't. Okay, so we have a Hamiltonian, and let's work. Well, let's see what it does. Okay, so it's mathematically equivalent to the Dicke model we started with. So let's think about a one photon state or one excitation state. So again, it looks exactly like what we had before. We simply create a photon at x and t and excite an atom at x and t with some density rho. And this is a combined vacuum state. Okay. So now the question is, in some sense, what are the equations of motion that are obeyed by psi and A? Right? So the Schrodinger equation, again, tells us what those things are. And they obey now these non-local equations, right, where the square root of the Laplacian is inherited from the underlying Hamiltonian. Okay, so this tells you how the light evolves. If there's no coupling, there are no surprises. And this tells you how the atoms evolve. Again, if there's no coupling, there are no surprises. And the coupling here allows for the interaction between the light and the atoms. Okay. There's also a normalization condition, which is inherited from the rotating wave approximation. So there are no virtual states, as people say. Okay, so these are our equations. And the first question we should ask is, can we get the usual physics out of this, right? So let's think about a single atom with density rho, which is now a delta function. Put it in its excited state and solve the equations. So you can do this, and what you find is that the atomic amplitude squared decays exponentially in time with the same rate that we calculated classically by Wigner and Weisskampf. And again, we have to make some kind of pole approximation somewhere in this calculation in order to make this happen. So this is good. We get the right answer. What happens if we have a constant density of atoms? Okay. So then we can solve these equations again. Here, rho 0 is constant. Let's suppose we have a localized region of excited atoms with some size Ls. We solve the equations. This can be done explicitly. That is to say, we don't have to make any kind of Markov approximation to do this. We get some formulas, which I wrote down just because they're there. And you can see what happens. So here we recover the oscillations that we saw in that figure of Scully's, which was, I will point out, the result of some kind of numerical simulation. within what is roughly speaking a couple dipole approximation. Okay, so again, there's some physics here which we seem to be able to reproduce. What happens if you have many atoms? So this is the problem of, in some sense, solving the couple dipole equations. Well, it turns out that some mathematics can be done here. So this is mainly Jason and Monis and Jeremy. And you find that the atomic amplitudes, well, they have a part which decays, they have a part which oscillates, but you can very explicitly figure out at long times that there is an algebraic crossover from exponential decay. And this could be, if you like, phrased as a theorem, by which I mean that all of this is justified. Okay, so in principle, we can understand what happens when we have lots of atoms as well. What happens if we have a random medium? Okay, so now this non-local system has a density of atoms rho, which has a part which is fluctuating spatially, which I call eta, and has prescribed correlations. Okay, and what we want to know, in some sense, is the average of the probability of finding an atom at x and t, and that is excited, and likewise the probability of measuring a photon at x and t. And so here the idea is that we can deal with this using much of the same technology that can be used in classical optics that was described in the book with Carminati. So I won't tell you the details, but I will simply point out the rough idea of what goes behind such calculations. So the observation is that these amplitudes oscillate rapidly on the scale of the wavelength, but we're interested in propagation over large distances where the density rho is relatively slowly varying. Okay. So in that regime of high frequencies, weak disorder, this means that that C can't be too strong. I'll come back to this in a minute. You are exactly in the regime where radiative transport theory works. Okay, and we can show that the analog of the radiative transport equation for these two quantities can be obtained by the same kind of asymptotics involving the Wigner transform. So the Wigner transform, let me remind you, is now a Wigner transform for the pair of fields psi and A. It's a 2x2 matrix, and if you just look at if you integrate over one component and you look at its diagonal, then you get the quantity you're interested in. This is psi squared, and this is A squared. It's worth pointing out that although the diagonal elements of W are real valued, they're not necessarily non-negative. But this is a consequence, it turns out, of the asymptotics. They become non-negative. Okay, so what are the equations that we end up with? Well, it turns out that the average Wigner transform can be decomposed into modes. And these modes, which I call A plus and A minus, which are written in terms of some deterministically known quantities, obey kinetic equations. Okay? And the kinetic equations that are roughly like this. So you have what you expect. You have the usual time derivative. You have a transport term. And then you have a kind of a kinetic term, a scattering term, which accounts for gains and losses into each of these modes. And where do these things come from? This scattering kernel and this scattering coefficient, if you will. Well, they come out of the theory. They are not put in by hand. They are given in terms of correlations of the disorder explicitly. So you can calculate these things. Okay. So let's see how this works in practice. So suppose the atoms are in some kind of excited in some kind of small volume, and there are no photons present in the field. Then you can solve the radiative transport equation at large distances and long times by means of this whole diffusion approximation. And if we do this, what you find is that these guys decay algebraically. All right. And here's a plot of the solution. You should forget what happens at short times because this is where the diffusion approximation breaks. And you can see something like the rapid rise and decay of the light, which you would expect from so-called single photons of the radiance. Okay, what about two photons? So this is where things get interesting. And here I emphasize that there can be entanglement of the photons, of the atoms with the photons, and so forth. So we consider a two-photon state, which has a two-photon amplitude psi 2, a atomic amplitude A, and psi 1 is an amplitude which allows for the excitation of one atom and one photon mode. By entanglement here, I just mean the factorizability of these various amplitudes. Okay. So now we need to do the same thing. We need to find out how it is that these amplitudes evolve in time. And again, the Schrodinger equation, in combination with Hamiltonian that we started with, give us a system now of equations. So this is the two-photon amplitude. As you can see, it's like a two-body Schrodinger equation, except the Laplacians are replaced by square root of Laplacians. These are the couplings, and so on. So what can we do with these equations? Well, for the case of a single atom, we can get the standard results involving stimulated emission. And likewise, for the case of a medium with constant density, we can, again, solve these equations explicitly. I won't show you that. This is the two-photon constant density plot. And again, you see results that are similar in spirit. And we can get a two-photon radiative transport equation. So again, there are now two kinetic terms, two transport terms, and some kind of very complicated transport kernel. There are four such equations because you need four modes to deal with this system. And you can write it all down and solve them in some kind of diffusion approximation. If you do this, and I'll show you an example in just a moment, we start with an initial state, which is an entangled state of the photons, which looks like this. Everything else is zero.
Just for the equation that we just wrote before,
yes.
Transport photon state.
Yes.
It's different if you have an entangled initial state, but it's the same.
It's the same equation. Yeah, the entanglement in this case only comes into the initial conditions. Yeah, and of course, what happens to the solutions afterwards is something that we don't fully understand. In fact, we would like to understand.
So John, if you generalize it to n photons that you're solving.
Oh wow, that's hard. You get a lot of equations. They grow quickly.
But the structure.
I don't even know. We sort of stopped at two. It was like one too many. Okay. But yeah, I mean, somehow to me, all of the physics is in two photons. And once you get to a lot of photons, somehow it's all classical again. And when you have 3, 4, I don't know, it's complicated. So, okay, so you solve them and you work out the asymptotics of the solutions. And now you get 1 over t cubed instead of 1 over t to the 3 halves decay. Maybe not completely surprising because you doubled the number of excitations in the system. And you can work out what happens and plot stuff. And so this is a plot. Again, you see the flash and the decay. Forget what happens at short times, and so forth. Okay, how are we doing on time? Speaking of time, we're doing okay. So we have a formula. Yes. Sure, Charlie. How far?
So we should forget what happens where the probability densities become negative?
Yes. So this is an artifact of the so-called diffusion approximation to the transport equation. If you try to solve the transport equation better, then this will not happen. What happens is that there's an initial layer and a boundary layer which contaminate things at short distances and short times. So this is a kind of an artifact of the boundary conditions which are needed for the transport equations. This is a well-known phenomenon, even for classical light.
Let me ask you
Yeah.
Why is it that you have the absolute value of K as the energy of the state, and so you end up with the square root of Laplace?
Let me hold that for the end. That's absolutely the right question, but I'm almost there. Think about, let me give you a very short answer. Think about the dispersion relation for the wave equation. That's what this is coming from. Okay. All right, so once you have this kind of, if you like, mathematical reformulation of what happens for scalar QED, there are lots of other questions that you can ask that I don't really have time to discuss, but there are papers. So you can ask, first of all, for deterministic systems, what do the resonances look like? Are there bound states? And so forth. We have a fairly clear understanding of this question for one photon, but not so much for two. Suppose the atoms are arranged periodically in some kind of an array. What is the corresponding band structure for such a thing? We have to think about band structures now for equations with pseudo-differential operators. It's not entirely clear how this works, but there are answers to these questions. What happens at large scales? Can you homogenize these equations? Again, the answer is yes, at least for single photons. Anderson localization. What happens here? Again, you have long-range interactions because of the square root of the Laplacian. It turns out for sufficiently strong disorder, for one photon, there is Anderson localization. The question is open for two. Jason and Monis and Jeremy have worked out solvers for these non-local PDEs, fast solvers using, what's the best way to say this? Technology that is very well understood in CCM. Okay. Might even have been developed there. Okay. We've also done a lot of work on waveguides. Waveguides are not one-dimensional problems here. Waveguides can be bidirectional, they can be chiral, they can be coupled. We know many things about this kind of problem as well. And finally, let me mention, of course, that I got interested in all of this because I wanted to know whether or not quantum states of light could be useful for inverse problems. I don't know. But I can tell you the kinds of inverse problems that we encounter here are very strange because the PDEs are non-local. And so the boundary conditions are not standard boundary conditions. So in particular, they are also non-local. So what this means is that it's possible in some sense to get internal information about solutions to such equations precisely because of the non-locality. It's almost as if you had the data everywhere inside. Now, you only get this by some kind of analytic continuation. It's called unique continuation for these kinds of equations. But in principle, you have access to information that you have no business having access to otherwise. Okay, so we have some thoughts about this. Applications. Well, so I'm interested in exploring what kinds of possibilities arise from thinking about quantum optics in this way. Quantum correlations here are the natural target. One wants to think about Hangel-Mondel type interferometry, so correlations of the counts of two detectors, and there are claims in the literature that at least for direct imaging, by which I mean nothing involving inverse problems, that you can get super resolution. You can beat the diffraction limit by a factor of 2 if you have 2 photons. Maybe this is not more than a party trick, but it's kind of cute, and I mention it. Something I'm perhaps somewhat more interested in, but know very little about, is possible applications to communications. So 2 photon states, entangled states, are used as the resource in some sense. And well, what is in some sense, channel capacity for some kind of quantum communications protocol? And how is it affected by disorder, by imperfections in the environment of various kinds? These are the kinds of questions I don't know how to formulate, but we might be able to answer if I understood a little bit more about that word, communications. Okay. And finally, here are some references. The basic model is described in this paper with Joe. There are some things on the archive and some other papers. There's more, but this is perhaps at least a sampling of such things. And I'll stop here. Thank you. Yes.
You were mentioning this entangle.
Yes.
Let's assume that it's running. Have you looked into this, the effect of decoherent induced by disorder, that at the end of the run, the system becomes not entangled?
Yeah. So that's, of course, the right question to ask. I don't have an answer to this question. So, I mean, in principle, if you measured, it depends on how you think about this. If you took all of the light, some kind of big 4-pi detector and count, you won't lose any photons. So in principle, maybe there's no loss of entanglement in some integrated sense. But there could be some loss of entanglement at points, right? And just the way in classical optics, when you interfere two beams, you can ask about what happens to the spatial coherence of those two beams. The spatial coherence propagates in some known way, and it can move around, but the light will remain coherent. So I think it's something like this, but I don't know the answer. Maybe you can help me. One somehow needs a measure of entanglement to answer questions like this. One way to think about this is to take the amplitude psi2 for two excitations, and think of that as an operator whose singular value decomposition you could compute. From this operator, one might be able to understand what the singular values are and then compute the entropy. That could be a measure of entanglement, and one could ask, what happens to this measure of entanglement as the system evolves? I don't know. It's something I'm interested in. Yes.
So John, you mentioned simulations.
Yes.
Could you comment on that more? Are there any fundamental difficulties or basically one could carry out some sort of
So the simulations that were done at the Flatiron, you're asking about that. I would rather have Jason answer that question.
Yeah, I mean, I think if there's no great fundamental difficulty, you need to deal with sort of full history dependence from the way we do it is we kind of integrate out the photon degrees of freedom, which sort of are on an unbounded domain, and you get an integral formulation that's fully history dependent, and we have ways of solving it. So I think that's
So to expand on this just a little bit, thanks, Jason. The integration out that he's referring to is the standard way that one gets to the coupled dipole model through these things. However, the history dependence is ignored. One makes a sort of Markovian type approximation. What Jason is saying is, because in some sense the atoms are not everywhere, you can solve this problem on a finite domain.
To a physicist, the result asymptotics for n atoms in a finite space is a power law and not exponential. It's very weird. I would normally expect for a finite system there's an interesting intermediate asymptotics, which is a power law, and it's some kind of long time because you're dealing with a finite system and you're far away and it was all long ago, it just looked like a point particle. So is there any intuitive reason why the power law stays to arbitrarily long time?
I think this has to do with the breaking of the rotating wave approximation.
Okay, all right, thanks.
Basically, just in that you break it, you get expansion.
Okay.
Yeah, and in fact, for single atoms, this is known. I mean, it's been done to death. Not very well, I should say. You're having fun. Go for it.
There is always this discussion about how the light that is coming to your
Yes.
atom is being absorbed and then emitted.
Yes. Yes.
However, an open question now is what happens when entangled light comes to a single atom. Because you are using linear response theory.
Yeah. Yeah. Yeah.
So
So
there is a lot of debate about which are the equations one has to do that case of two photons. Second order response.
okay, so I don't know the answer to this question. I'm going to say something that's probably wrong, but maybe not. So if we go back to the equations for two photons, then for the case of a single atom, we are describing something like simulated emission. The way this is handled is through initial conditions. So if we have an initial condition which is entangled, something would happen. We haven't explored this possibility. But I think it's fully analyzable in this picture. Again, without any approximations, other than rotating wave.
I was a little bit confused several about
Yes.
Because Anderson localization of the scattered light on randomly distributed atoms, if I understood you correctly.
Yes.
But what confuses me is the fact that for Anderson localization, you have to keep the phase information over all your scattered paths. And if I imagine you have an atom, and that atom is excited by absorption, and then you have emission, how do you preserve phase information? Especially if it seems spontaneous.
Well, so this is no different than what happens with classical light from the point of view of the light. But you have in your mind, of course, this quantum picture of how the light is being absorbed and re-emitted, and I'm not, in fact, really sure that that's the right way to think about this.
But you can have like scatter, so you can have like this A squared contribution of your minimally coupled Hamiltonian, which you actually did not have. And that I can imagine preserve space information, just scatter.
Yes.
But here it's absorption and then spontaneous emission. And the phase information should be, I don't know, over your emission rate.
Yeah, I don't know how to answer your question. All I can tell you is that we can prove that there is Anderson localization. Now, you might ask me what I mean by that. And there are two meanings to this. So one is the statement about the spectrum of that operator. And the second meaning is something about the dynamics, that it is subdiffusive. I don't have a physical picture of the kind that you're asking about. I'm sorry. I actually find Anderson localization confusing. So maybe you know this. There is kind of a physicist's version of all of this, and then there's a mathematician's version of all of this, and they don't completely connect. I don't really understand either one well enough to complain.